So, welcome. This is the talk about Elm, so if you're in the right room. Subtitled it Functional Programming for the Web, which, okay, the web is a big, umbrella, so really it's functional programming for client-side web app development fundamentally, but this is a little bit more grabbing. So I assume that, who here has heard of Elm before, maybe even used it? Anybody? Okay, so it's not totally unfamiliar to people, which is good. I mean, it's introductory, but I try not to make it too tedious in that sense, so hopefully I'll get the main points across. My goal here is not to teach you Elm so much as it is to orient you and show you what it's kind of, the big moving parts in Elm and why it's interesting or important. My name's Austin Bingham. I work for and part own with this fellow, Rob Smallshear here, 60 North from Norway. And last year, if you were here and you were at the lightning talks, you might have seen a lightning talk I gave on Elm. So 5 minutes of getting laughed at for saying that you should use Haskell for web pages. Everybody thought that was very funny, but haha. Now we've written the schedule app in Elm, and it's actually a very pleasant experience once you get past the bumpiness of learning the language and the fluctuations in the development process that are going on with the language itself, which have mostly settled down, and we'll talk about that a little bit. But I found Elm to be very, very joyful. I learned about Elm when I was in the midst of learning JavaScript and Angular and in a big project that I was hating because it was a monster that was unmaintainable for no good reason except that JavaScript didn't strike me as a good language. It was hard to grow, I felt. And Elm addresses a lot of these pain points to me. So a bit more about me, I suppose. I'm originally from Austin, Texas. This orange dot you really can't see, the home of the University of Texas Longhorns, go Horns. It's a very pretty city. This is a statue of Stevie Ray Vaughan, one of our local tragically dead rock and roll blues heroes. Great place to visit if you like live music, if you like Mexican food, or just food in general, and it's a very nice place to hang out in the parks. About 8.5, 9 years ago, I moved to Stavanger on the west coast of Norway. It's a different kind of landscape. If you watched the show Vikings, and there's the scene when Ragnar became king, he was sitting on a rock right here looking out over the fjords. That's my backyard. It's about 30 minutes from my house, so my backyard per se, it's closer to me than it is to you. And we have different kinds of statues there. These are the three swords, the statues of the three swords that commemorate the unification of the kingdom of Norway. Again, if you watched Vikings and you met King Harald, he's the guy responsible for those, not building them, but uniting the kingdom. That's my understanding, at least. Anyhow, and this is where 60 North is based. We're in Oslo and Stavanger, so we got the country covered from east to west. So yeah, that's a bit about me. You've probably seen a link to it or heard about it already, but there is a conference app written in Elm that is the basis for the latter part of this talk. So you can just load it up in your browser at our From 60 North's website here, and I think that link has been around, and you can get the code for it here. It's all open source and everything like that. And I'll have a slide of links at the end as well. The main reason I show this is, A, that you might want to see the code later on or as we're doing this talk, because we'll actually be going through a bit of it, but also let some help. So if you want to pitch in and learn some Elm, it's a great place maybe to get started. Right, so our agenda is maybe a bit optimistic. I think we'll get through at least parts of all of these. What is Elm? In a broad sense, why would you care? Where does it fit in the world? A little bit about the language itself. And then I'll give you a quick taste of what an Elm program is like, minimal, Hello World-ish style stuff. Then we'll look at something called the Elm Architecture, which is this prescribed, almost mandatory way of building programs in Elm. If you go and you learn Elm from any tutorials or you read any blog posts, they will mention this and they will be very explicit about this is the way the program are structured. And you can, in principle, write programs other ways, but it's unnecessarily difficult, and you don't really gain anything in my experience. We'll look at some specifics, some specific things you might want to do, specifically talking to the web, so doing HTTP requests, fundamentally, JSON decoding and encoding, and we'll look at JavaScript interop, because these are two topics that almost every Elm program that's on the web at least has to do, and they can be a little bit painful for new people. So I want to not spend a huge amount of time on these topics, but show you how it's supposed to work as far as I understand it. And then we'll finish it off with a tour of the ACCU schedule app. The point of this is to not go through every line of code, obviously, but to revisit the elements that we talk about here and show you what they look like in a real program, right? And so hopefully the idea in my head, this is the first time I've given this talk, is that you will be able to leave this talk, look at the code for the ACCU app, and see how all the parts fit together. So it's not abstract, it's very concrete, and you can actually run the app and see, oh, this is what's going on here, and you can map that to the source code. So maybe it'll be successful, maybe not, but I think it's a nice way. And I should thank Russell for giving me the idea of writing the app in Elm and then using it in this talk. It was a brilliant move, and fortunately it all came together in time. So what is Elm? I mean, most of you raised your hand when I asked if you had seen it or used it, so you probably have some sense. So I want to approach this with the way I approached Elm. What is wrong with JavaScript? What do you guys not like about JavaScript?
No types.
No types, okay?
Or runtime types.
Yeah, yeah. That's not the only problem with JavaScript. Yeah, the sloppiness is a big part of it to me. It's aesthetically unpleasing. It's improving, but it's certainly not great. There is that, yeah. It's it triggers your brain to not be pleased. Yeah.
A lot of the semantics seem to have been only formalized afterwards, so it's
yeah.
very like post-hoc semantics.
Yes, it's the sloppiness again. It's okay. I have a nice metaphor we're leading up to here, so this is good. You're playing into my hands. So. Common complaints, and these are really my common complaints about JavaScript. Hopeless type system, right? Okay, it just doesn't give you any help at all, and it adds numbers and words together and gives you things, and then you're passing around null references that kind of work but don't really work, and all sorts of things are going on that just feel like we could have done so much better. The most popular language on the planet that runs everything is this horrible thing. Bolt-on modularity. I hate not having a module system in a language because it's such an obvious thing. It's a problem we solved decades ago. We know how to do it in other languages, Python, my favorite. And so they have all these ways people have invented to bolt modularity onto the language, but they don't interoperate, and you have to have these really crazy codes sometimes to say, well, maybe it's CommonJS, maybe it's whatever other flavor, and it's frustrating, and it is just more friction in the system. There's very flavor of the week. You know, I happen to know Angular, but apparently Angular is not cool anymore. It's React now, or Vue, or Elm. You know, it moves so fast that you really don't know what the new stuff is. You never feel kind of up to date. It requires tests, but very often JavaScript stuff, the front ends at least, are hard to test. It's pretty easy to unit test JavaScript stuff, but testing from the front end requires WebDriver and this whole string of complicated technologies that you can get to work, and they're kind of fascinating, but it's harder than it seems like it ought to be. Unexpected runtime errors, of course, everybody's seen these. And it's not really one language. This goes back to flavor of the week. Most people, if they're a JavaScript programmer, they're actually an Angular programmer or a React programmer. They can't really function that well outside of their system because these frameworks bring so much with them, module systems and dependency tracking and all that kind of stuff. So it feels like a bunch of islands that kind of communicate a little bit. The metaphor I like, if you've never seen this movie, you should see it. There's a movie called Idiocracy. And the point is, he starts off, he's in the army. And he's been calculated to be the most average person on the planet. So they freeze him in this experiment for suspended animation. But then they forget about the experiment, so he's asleep for like 500 years. And he wakes up, and smart people have been outbred by dumb people, and he wakes up as the smartest person on the planet. And he has to teach them not to water their crops with Gatorade and things like that. And I feel like he's JavaScript. JavaScript started out doing a perfectly fine thing, running code in a browser, and then it wakes up one day and finds out it's running the world, right? And so, we have to address all these. He has to, deal with all these things. So he is a very funny movie and a nice enough guy, but he's just in the wrong place, right? So I hope this metaphor strikes home. It seems true to me. So how does Elm help with these things? I'm going to hopefully convince you that each of those bullet points is addressed in some way by Elm. JavaScript has the hopeless type system. Well, Elm has a Haskell-inspired, though not quite as powerful as Haskell, type system. It's statically typed, and the compiler tells you when you've screwed things up, and it turns out to be really, really powerful for developing web APIs, web front ends, I should say. It has a very intuitive native module system. If you've used Python or Java or any other C# languages that have module systems, you'll feel right at home with this one. It just works. It has a set of prescribed patterns, and it's very opinionated on how you're supposed to do things versus flavor of the week. So if you write Elm and you look at somebody else's Elm program, you're going to see those patterns repeated over and over and over. And it's very, very nice. It makes it very easy to read things. It can feel constricting, but one of my favorite quotes, I think it comes from the art world, is that form liberates. If I don't have to think about whether I'm doing a chalk drawing or a painting or a pencil drawing, if I've been told that I'm going to use a red pencil on yellow paper, then I'm liberated. I can make great things. But if I spend all my time analyzing how to do what I'm supposed to do in this meta-analysis, you run out of steam very quickly. Far fewer tests are needed. And if you've ever coded in Haskell, for example, maybe I'm wrong about this. Maybe I can be proven incorrect. But when you have a type system that's that sort of watertight, there's very far fewer things that you need to account for in your tests. You know that you can't have null dereferences. You know that your case statements are complete because the compiler won't let you by without filling in your case statements. You still do need tests. You can screw things up. And some of the things you can screw up nowadays, hopefully they'll fix with advancements in the compiler and the language itself. But I find that, by and large, I don't really need any tests. I have some, like for the ACCU website, I have a few WebDriver-based tests to just make sure that, when you click a card, it takes you to the right description and things like that. But beyond that, I'm not doing unit tests down in the base because I just know it works. I just sense intuitively. So hopefully I'm not completely wrong about that. I have no runtime exceptions. That's in quotes because that quote comes from the Elm language website. They claim this. It's not 100% true. There have been things like defects in certain libraries, especially those that interface with native code, JavaScript code. But by and large, you face orders of magnitude fewer possibilities of runtime exceptions in Elm just because of what the language gives you. And it is a single, I call it BDFL style language, the benevolent dictator for life. Like Guido is that for Python. They have this guy, Evan, who wrote the language and is controlling. He's got his hands on the levers. And so you get this one guy whose vision is being channeled into the language, and so it feels unified, much the way I think Python does to a large degree. I mean, it's a much bigger language. It's a much bigger community. But Elm still has that feeling of a vision being applied. So where does Elm fit in the world? You probably all have a sense of this already, but it's for developing web clients. And by and large, people will say single-page apps, but it's actually quite good for filling in parts of a larger site. So if I've got some website here and I want to redo this bit in Elm and this bit in Elm, they'll all work just fine. They'll fit very comfortably with your React code or whatever the rest of this stuff is. It's not an issue, and it's done very, very commonly. You can also grow Elm to be your entire website, like the ACCU schedule thing. It's all Elm, and it's talking to a little bit of native code in the back end, but it's not embedded in some larger JavaScript HTML program. So you can grow and use as much or little of Elm as you want, and this is really nice. If you've got an existing product and you want to start to maybe experiment with Elm, pick a piece that maybe doesn't have a lot of dependencies and just pick that and redo it on a branch somewhere. Excuse me. Who's behind Elm? It's got a very nice community. It's open source, obviously, like all cool languages these days. It's very active, fast-moving, and very welcoming. They have a really nice community of people who are ready to answer the question, any question you've got, even if they've heard that question 1,000 times already. They may just point you to a wiki, but they're not angry people yet. Yeah, yet. Elmlang.org, that's where you can find out that's the center of the universe. GitHub, Elmlang project has all the stuff that's core to the language, the compiler, the standard library, that kind of stuff. There's a Google group that's very active. This is where I get a lot of questions answered. It's very nice if you're into forums like that. And I have to call out Prezi. They employ the guy who writes the language. So I assume they use a lot of it. It's not really a resource for you. I just feel like I should thank them for giving time and money, basically, to make this stuff happen. It's this guy, Evan Shapticki, I'm not sure. It was his senior thesis, is where Elm came from. He was studying reactive functional patterns in web development, and Elm came out of that. So that's the short version of how to get involved. So we'll take a quick look at the language. Are there any questions before I move on? Good, good. So what's the high-level picture of Elm from a sort of technical language point? It's statically typed. So everything has a type, and the compiler enforces a lot of constraints for you at build time. It compiles down to JavaScript. They've talked about having compilers to other languages, but I think the core people in the language feel that they want to stay focused on just doing web client kind of stuff. They don't want it to become the next JavaScript that where you have Node and you have all these other places where it's running that it shouldn't be. And I think that's a good focus for them to keep. It has immutable data structures, so just like Haskell. It's inspired by Haskell. The compiler is written in Haskell, and so there's a very Haskell-y theme through the language. But immutable data structures, so you get all the benefits of referential transparency and things not changing underneath you and all that kind of stuff working in your favor. It's easy to reason about. Type inferencing, so that everything is typed, but you don't have to spell out the types of everything all the time if you don't want to. Commonly, you will, in your type signatures, say what you expect to come in, but it's not required. And the compiler is quite clever about figuring out what things are. Partial application, currying, function composition, all the kind of stuff you expect from a functional language is in there. And the way to think about it, and this is a very, very fair way of assessing it, is Haskell for web pages. And if you think in terms of Haskell things and you think in terms of functional programming, you can bring it in, drop it into your Elm program, and your mind will just work just fine. So it's a very pleasant experience to start programming this way again after you've been coding in JavaScript for any amount of time. There's a bunch of primitive types. You're not going to be surprised by any of them. Ints, floats, strings, chars, bools. And this is a young me at the Smithsonian imitating a monkey. So yeah, I'm not going to go into details here. They behave the way you would expect them to behave, I'm sure. And I've never been terribly surprised by any of them. Obviously, it's Unicode underneath for the characters. I didn't know there was a Unicode tree, but there is. It's not an Elm, but it's a... Functions also behave very much like you would expect them to behave. So multiply takes two arguments, x and y, and it's an expression, so whatever x times y is what's returned from the function. It's what the function evaluates to. You'll notice I haven't specified what x and y are here, and you don't have to specify the type signature, but if you, and Elm will try to figure out what the type is based on how it's used, and it can be pretty clever about that. More often than not, though, the recommendation is that you do supply a specification. So this is saying I need two things that are number-like, and I need to expect that same kind of thing to come out on the other side. So nothing shocking there. I can do partial application. I can say, so my function called double is just multiply with two partially bound to x, and just returns a function that takes a single argument now and doubles it. Again, you don't have to supply a type signature, but if you do, this one is now just takes a single number, gives you back another number. And finally, you can do function composition very naturally with sorry, yeah, I know it's low down on the screen, sorry about that. This is the function composition operator, so it's saying double and then double again, so multiply. And again, this is going to be very familiar to people who've seen other languages that are similar in shape and feel. So functions are pretty unsurprising, I think, very easy to work with and quite pleasant. There are a set of homogeneous iterable data types in the language. List is sort of natively built in. I don't think you need to even import anything to get access to lists in the language. So it just looks like square brackets, like Python. And they're homogeneous in the sense that everything in a list has to be the same type. So in this case, it's all integers. It figures that out. You can have tuples, but you can't have a list of multiple different data types. It won't allow you to do that. And there's not some base object type either that you can cheat with. There's a dict provided by a library here, dict, which is behaves like you would expect. It's a mapping of keys to values, and you create new ones with empty. You can insert with this function and blah, blah, blah. Again, I'm not going to go into detail on these things. I just want to kind of show you the highlights of the language. You have arrays, which are for if you have to fast index into data. If you have some numbers, maybe you need to be able to quickly fetch by index. And you can have sets, which are, of course, just unique values inside a list, basically. So those are available as part of the standard library, and the list is built into the language fundamentally. Oh yeah, I should have clicked forward. Yes, fast indexing, and you remove duplicates with the set. More interesting type, perhaps, is a record. It's really, I call it the workhorse of Elm because it's almost all models, data modeling is done by creating a record of some sort. It's name to value mappings is really all it is. So it's just like an object in JavaScript or a dictionary in Python, kind of. So you declare them like this, right? Nothing shocking. You give it a name and the type of the thing. And then very often, almost always, you will assign some type alias to it. So this is somebody's full name. They've got a first name and a last name. You say type alias, and the full name is this shape here. That's really the way to think about it as a shaped piece of data, because Elm lets you pass in things that aren't necessarily full names, but if they have first name and last name in strings, it's like, yeah, I know how to use that, no problem. It's a shape-based typing system very often. You can use your custom types then. So if I've created a record here, I can say, okay, well, that's a proper type now, and I can reference it in some other record that I create. And you get free constructors when you create so I've created the user type here, and that gives me a constructor. I mean, I'm abusing the term a little bit, but that knows how to take in a full name, which also has a free constructor, and the number 42, which is legitimately my age, so that's cool. I can actually use that number and not just be being cute. Yeah, I get that for a year. And you get free accessors too. So these dot accessors, that's just a free function, and if you pass it a user, it's going to extract the name, and then I compose that with dot first name, which then extracts the first name out of the full name record. So you get a few little niceties for free, and you'll see people use these fairly liberally because it's a nice compact way of passing around accessors and so forth in the language. You can't really see it, but that's Pink Floyd, The Wall Part 2 there. So this morning, I'm very susceptible to if somebody whistles a tune or says a song name, it gets stuck in my head. So after this keynote this morning, I'm kind of going a little bit crazy because I knew most of those songs, and now they're all kind of competing in my brain. And now, of course, Pink Floyd is in there as well. Another sort of fundamental data type, so to speak, is a union type, and these combine very well with pattern matching in the language. The subtext here, a natural way to model weird shaped data is a nice way to think about these things, and you'll see why. So I create a type called shape, not type alias, now it's just type shape. And I'm going to define a number of, I think these are legitimately called constructors in the language. So I can create a shape by calling the circle constructor with a float, or the square constructor with a float, or the regular polygon with an integer and a float. All of these instances, as a way to think about it, can be passed around in the program and match to the shape type. They don't have a common base class or anything like that. They just happen to be ways of declaring shapes. And whenever a shape appears somewhere in your program has to make sure that it handles every single one of these constructors, otherwise the compiler will complain. And this is a really nice feature of the language. So if I have a function called render, and it takes in a shape and returns a string, so it's not the greatest render function in the world, but you have a case statement that gets that shape, and you have to have a handler for each of these constructors. If I left off that, the compiler would say, hey, you didn't handle regular polygon, so you have an incomplete program, so I'm not going to let it pass. And this is one of the ways that Elm enforces your program being complete and correct by the time it gets through the compiler, because there's no way you've forgotten to do something here. You've handled the case. You've handled every single constructor case. And if I add another one here, of course, and I try to recompile, the compiler will complain again. Very often people have a match at the end. If they only care about circles and squares here, they might have underscore, which is the secret code for everything else, and then have it return some other string. But you have to, in some way, shape, or form, account for every member of this union here. So you can have arbitrarily strange constructors that seem completely unrelated, all under the same union. And it's a great way to model data that you want to relate logically, but don't have any structural relationship. They don't have any other relationship except maybe in your domain. So it's a good way of combining things without having to have tortured base classes and mix-ins and all that kind of stuff. Yeah, this has to be exhaustive. Sorry, I can't see what's supposed to come next because of the way it's set up. So yeah, this has to be exhaustive. If it's not, then the compiler will complain. Modules and importing. As I mentioned before, the module system in Elm is very intuitive. I found it very intuitive. I've never had to think really hard about it. It just worked the way I sort of expected it to work. So if I have a module here, so this is loader.elm, it's a bit hard to read, and I have to declare at the top that it's a module called loader, and I can tell it to expose only certain symbols from the file, in this case load. You could also say exposing ... and that would expose everything. So that's a module. And I can import that module in a number of different ways. I mean, really, they're all the same way. They just bind names in different ways. So I can just say import loader, in which case I can then call loader.load, very easy. I can import loader as L, and this is done very often with lengthy module names that are used a lot. Then you can say L.load, or I can say import loader exposing load, and I get load as a free function in a non-namespace function. I believe if you do this, you also get loader, just like here, but you expose, you basically boost up a few of the elements of loader into the local namespace. So there's no magic, nothing fancy there, but it's so much better than the options in JavaScript, I find. So that's the quick sort of tour of the language, and we did that, yeah, good time. So let's take a look at some actual code. So we're going to have to exit here. So I should orient you just a bit. So there's a program called Elm Reactor, and you'll hear all about it if you start using Elm. And it's a little web server that knows how to look at a directory full of Elm code and compile it, and then show it in your browser for you. So it's great for prototyping and so forth. So I'm in a directory that contains a bunch of Elm code. Now it's serving up on localhost 8000, which is here. Right, so I see all of these Elm files. So let's look at one of these Elm files in Emacs real quick. I need to go back to Elm presentation material. This is that guy, right. So this is the hello world. It doesn't say hello world, sorry, of Elm. So I have my main function. It has to be called main, so they stole that from C. Smart guys. You can't see it. Sorry, I need to lower this down to. You can't see the top, but there it is. Import HTML, right? Yeah, this is just-in-time presentationing here. Presentationing, it's a new word. So what's critical here is we've imported HTML. You can't see it at the top. HTML exposes a function called text, which just spits out some text in HTML. And we've told Elm that main is returning in HTML.html. That's just their HTML object, or the type, that the Elm runtime knows how to then render to actual HTML. And I've told it, show me hello. So what does that look like if I execute it? I know you're on the edge of your seat to see what that looks like in real world. In the real world, lo and behold, right? It's incredible, right? So it gets better though. So wonderful, thank you very much. Oh yeah, nailed it. Okay, cool. The next one is a broken hello. So this may seem like an unnecessarily complicated return signature. Why can't it just return a string and have that show up? Well, the reason is that it can't. Elm doesn't let you. If you try to do something like that and outsmart it and just say, main return hello, it's gonna fail, and it fails in a pretty spectacular way. It says main value has an unsupported type. It said you're trying to return a string, but the only things that I expect out of main are HTML, SVG, or program, and we'll talk about program in a bit because it's the most interesting return type. I've never tried the SVG one, but it's complaining. So the compiler has told you you can't do what you're trying to do because that's how the language is defined. Great. We move on to functions, and that's way too big. Right. So we looked at functions earlier, and there's nothing crazy going on. Let's start with the simple one, punctuate, that takes in a string and another string and returns a string, where the first argument is your punctuation mark, and the rest is your sentence, and it punctuates your sentence for you. So, and you've all been dying for this function, you're welcome. It's open source, so now you can use this. Exclaim is just, in fact, this is more complicated than it needs to be, I believe. It is, yeah. Exclaim is just going to add an exclamation point to your sentence, so it's going to just automatically drop in an exclamation point for you. So this is just, there's no rocket science here. Just want to kind of show you how these things are generally kind of constructed. You often have a very general function at the bottom, then gets partially applied to and curried and all these things to be more widely applicable. So, and here in main, we pull the same trick again. We say, I want to exclaim hello world and turn it into text. This is the apply, forward apply. So it says, call this, take its return value, and then pump it into this. You'll often see, 5 or 6 of those kind of chained together. And it's really easy to read. Once you learn what these symbols mean, it's really easy to see the logic because everything just kind of flows in. It's like pipes. It's very, very pleasant. So does this actually work? I'm sure you all believe that it does. Yes, it says hello world. Okay. And I'll have a link to all of this code too, by the way. I mean, if you want to take this home and try it yourself, these terribly unexciting programs. Right, is that not quite readable? Okay. So here we start using a union type. So we have punctuation. We said the only punctuation we allow in the system are periods, question marks, and exclamation marks. And now the punctuate function takes in a punctuation symbol, here, constructor, and a string, and then it uses a case statement to say, okay, what's the actual string I'm going to use at the end, and then it does sentence plus punctuation mark, whatever it is. And exclaim now becomes much simpler. We say, well, that's just punctuate with an exclamation mark. And that returns a function that takes a string and returns a string. And then we have our main function here that you can see has no type signature. Any Twin Peaks fans? Yeah, so the new one's coming out. It's going to be awesome. So the owls are not what they seem, right? So we're on union types now. So ta-da, okay. I want to integrate this better with Emacs so I don't have to bounce back and forth, but it is what it is right now. Here's how records look in action. Emphasis on in action. Yeah. So here we're starting to build our publishing empire, right? We said we've got our punctuation union, now we've captured the idea of a sentence in the data structure, and we've captured the idea of a paragraph. We're saying a paragraph is just a list of sentences. Okay, that kind of makes sense. And we're saying a book is a title and a list of paragraphs. Yeah, it's pretty broadly applicable. I can imagine publishing under this regime. And the rest of the functionality is very much the same. Let me close that so we can see more. Main is a bit interesting, though. Here we see, this may be our first example of a let block. So let lets you create a block where you can assign variables fundamentally. I shouldn't call them variables. You should map names to the values because they can't vary. So P1 is our list of sentences. So I just say sentence, da-da-da-da, another sentence. And then a book is a title and some text. And let me format the book. Is that correct? Because the text is supposed to be a list of sentences. So I think this, I talked myself into a loop. I'm sorry about that, but it does work. Because if I run it, we get this. And this is just, more Elm, just getting fancier and fancier and applying what we saw here. Right, that's what it is. Okay, all right, so we have one paragraph. Thank you very much for that. The HTML magic is all happening up in here. And even if you've never used Elm, but you know HTML, you should be able to read this fairly straightforwardly. You have a div with no attributes. It contains an H1 statement, or H1 tag inside that, printing some text. That's our title, so we're just making it big. That's H1. And then we are mapping our paragraph formatter over, and then joining that up with HTML text. And this is going to give us a list of HTML text objects with our text from our paragraphs, and then we're going to call b.text, which is the book. Right, this is the text from the book. So the details don't really matter. I'm just trying to give you a flavor of kind of how it looks. And you'll see a lot of this kind of code in the views of your Elm architecture programs. And the beauty of it is that it's all strongly typed, it's all safe, it's all going to, in some sense, look right when it's displayed. You can't screw it up because it's all done in Elm and just producing HTML on the end. So you know that if your program compiles, you're almost certainly producing at least valid HTML and stuff that's not going to throw a bunch of null pointer exceptions and things like that. So those are records. Modules. So modules just takes some of the details that we looked at before and puts them into separate modules. So this is now just the main function, and you can see that we're importing publishing.books and publishing.punctuation, which we don't need to look at, but you can see over here in the tree that I've created a publishing directory with 2 Elm files, books and punctuation. Those become the module names, and in fact, Elm will complain if, for example, so this is publishing.books, and if I'd called it module publishing.texts, it would complain. So you have to match the name with the file name, which makes you wonder why they force you to do this in the first place, but they do. But it's not a big onerous problem. It's the way the language is. And we saw that it works, right? It's still a nightmare on JavaScript lane. And that is our last example. So that's the quick tour of Elm in action. We haven't seen one main thing, which is the Elm architecture. So we have a whole other section on that. But when you go after this talk and want to sort of see how programs are built up and constructed, I hope this is a nice little narrative that you can refer back to and see the bits and pieces in action. All right, so back to the presentation. The next sort of main topic, and one that's very central to how Elm is constructed, is what's called the Elm Architecture. A note on this picture. So I saw Kevlin Henney gave a talk at NDC London, and I was transfixed by one of the backgrounds in one of his slides. He was talking about architecture, and it was this picture. And I didn't know what it was from, I didn't ask him, but I happened to be with my girlfriend the next day at the Harry Potter experience in wherever it is near London. And that's where it's from. There's a wall with all these diagrams of how they built the sets, and it was one of these pictures. I snapped it, and I was very impressed with myself for remembering it. So yeah, there it is in the background. It's a nice it's Dumbledore's office if you're nerdy enough to care. I don't really care, but my girlfriend loves Harry Potter, so I know all about it. This is, I think this captures the essence and spirit of the Elm architecture, the idea of how it's supposed to be put together. You have some idea, some notion of a model. Typically, this is one of those records that we saw, right? And it contains the full state of your program, the full state of your program. You have some set of messages. This is a union type, and each of the constructors for that represents some change that can happen to your program, some way your model can be changed, or some piece of information coming to you from the Elm runtime, so from JavaScript land. That may have been initiated by something you put in your view or something you did in your update, but what happens, you have this update function, and its job is to take in a message and a model and produce a new model. Generally a brand new model. Sometimes the model stays unchanged, but it produces the next model that's going to then be pumped through your system, right? So update is often one of the most complex pieces of your code because it's the thing managing all the state change in your system, but it's completely decoupled from your view. It's completely decoupled from, well, the rest of the program, and this is by design. This is not revolutionary. This is, our instincts about how MVC is supposed to work are very much along these lines. But it's a nice, simple, easy to understand, easy to reason about way of putting programs together. So if you have a view, which is optional, but most programs do if they're web front ends, it receives your model, renders something, typically HTML, but could be SVG, which gets passed down to the Elm runtime, which is the JavaScript land that we don't typically need to mess with. Your update function can produce things called commands. Commands are just boxes for more messages. They are a type wrapper around message that prevents you from introspecting messages. I don't really know why they have them, because they kind of get in the way, but that's how it works. You spit a command out with a message that will eventually result in that message coming back out on this side. Or I should say, this will result in a message of this type, one of those constructors coming out this other side. And it's just this loop. This is it. This is how Elm programs are put together. Model, messages, update, view. There are some problems with this, of course. I mean, it is a bit simplistic, and sometimes you run into real problems correlating the bit of code, the bit of logic that produced this command and the message that it ultimately results in. You end up having to put correlation identifiers and things and finding some way to know how to map those together. And that's an ongoing discussion in the community, and it can be a bit of a pain point, but it's not hugely painful. The payoff, of course, as I've kind of tried to make clear, is that you get this very simple, very easy to reason about model of how your programs are put together. So at a very, very high level, this is how most Elm programs are shaped. How does that look in code? And this is kind of the order in which, I haven't written like scads and scads of Elm code, but when I start to approach a new project in Elm, this is kind of the order that I think about things in. One, the shape of the data. I define my model. Right? It almost always has an ID and has some list of things and maybe reference to another thing and a view model and all this kind of stuff. But I think about the shape of that initially. And often this is drawn from the domain that you're trying to implement something in, right? So I've been working in orthopedic surgery right now, so maybe I'm thinking about modeling fractures or something along those lines. So I kind of write down what I think it's going to be shaped like. And then I think about how it's going to look. Because I can create my view just knowing what my model looks like. I don't have to worry about how to update my model. I just think about, well, given an arbitrary model, how do I render it? And I do that. Because very often that's, especially if you're working for somebody else, they've given you an idea of what they want the program to look like, the front end. They don't care about the back end, but you're given some ideas here. So these actually kind of get developed in tandem as you think about, well, the view is going to be like this, and this is going to appear, and this is shaped here, blah, blah, blah. That influences how you make your model. But you can do these things without thinking about the rest of the mess of updating the model and all that kind of stuff. And then I think about how it changes. And this typically, so when I say how it changes, I think about what are the messages in my system, and how is my update function going to take those messages and create new models for me. These typically get created, in my approach at least, sort of hand in hand. I feel like I should be smarter. I should be able to think about all this stuff ahead of time, but I typically can't and find it doesn't impede me too much. And a lot of times also I find that the messages in my system, I figure them out as I'm making the view, because I'm like, okay, if they push this button in the view, something has to happen. Oh, I need a message that means blah, and then I create a message, and I have to then update my update function to handle it. So the update function is almost always shaped like this. It has case of the message type, and then a handler for each one of those typically calls some other function. But that's the shape of your update function. So it's very straightforward, a few moving pieces, and you can very quickly get something on the screen, which is nice. And I've long been a fan of, it's not quite a tracer bullet approach to things, but of being able to get a skeleton program in shape without having to have the entire universe of the program. It's motivating, it's fun, you find edge cases, it's a great way to build programs. One of the reasons I like Python is I can do this. I don't have to think about a whole lot of stuff. 90% of my Python program can be broken at any point in time as long as the 10% I care about is working. And that it allows me to move very rapidly. It's a very different language from Python, of course, but kind of get the same feel if you take this approach. Subassembly is required. You have to bolt all these things together. So you get your view, your update, your model, and all these kinds of things, and you have to have some way of making sure that the plumbing is then connected to all those. And so I stole this from IKEA. I think I'm illegally showing you this picture. I apologize. But that's where yeah, don't tell anybody. That's where the main program comes in. So main, we see in main that returns HTMLs, but now we have a main that returns a program. And a program fundamentally is something that has an init function that takes an initial model and any messages we want to do immediately, a view function, an update function, and subscriptions, which we'll talk about. They're basically how you get messages out of things like WebSockets and stuff in JavaScript land. And this program's job is to take all the things you've provided and then put the plumbing together and spit this program out that the runtime knows how to use to then run this cycle forever and ever and ever. And so when I say that the Elm architecture is effectively prescribed, it's because this is how you're almost always going to put your programs together. Unless you're a masochist and want to create your own program for some reason, which there's probably good reasons for it, but I can't think of any, you're going to use one of these, and it's going to force you to make an update and a view and a model and messages. So we can kind of see what all these parts are for. This is the standard type for main program. Flags we'll talk about as a way to get initialization data out of JavaScript. Your model, whatever its type happens to be, your message type, whatever it happens to be. You need to provide an initial model of some sort. Often there's just a function called initial model that returns that. Initial actions. And so an example of initial actions would be in the ACCU app. For example, when the program starts up, we have to make an initial fetch from the web server to get data about speakers and so forth. So I kick off a couple of messages from here saying, go get that information. And it ultimately arrives to me in my update function where I say, oh, new data, and drop it in the model. Your view function, your update function, and messages from JavaScript. So these subscriptions, we'll talk about those in a little bit. So this slide, plus the previous slide, is how almost all Elm programs that I've seen, if they're not like libraries, if they're not utility libraries or something like that, are put together. So is this reasonably clear? Nobody's in the fog? Okay, good. So what is program? It's essentially factories for bolting these things together in subtly different ways. And I think they're actually kind of stacked on top of one another. So there's this notion of the platform program, which comes with Elm, the standard library. And it's essentially a program without a view. So it's everything minus a view. So if you wanted to write some kind of program that in Elm that interacts with JavaScript, it doesn't necessarily have to have a UI. This is the kind of program to use. I've never written one. I just don't have the need to. Typically, if I'm writing some other kind of program, I'll use another language. HTML.program is the one I've used almost exclusively until recently. And it's the one we saw that binds together a view, update, and produces HTML that gets rendered to the screen. Navigation.program is like an HTML program, except it also embeds a notion of internal navigation inside your single-page app. So it takes over the routing of certain URLs. Otherwise, it's just like an HTML program. And when we look at the ACCU app, we'll see this is the one we've used because it has a fair amount of internal navigation. But fundamentally, it's not much different from HTML program. So it took me a while to pay enough attention to understand what these were all for. I got quite far in Elm without really paying attention to what program really was supposed to be all about. So I just wanted to get these up here so maybe you can have a head start when you start looking at things. But most of your main programs will be shaped like this. It's some kind of program has to be coming out. These all return a program type. So these are functions, program.program.program, that all return one of these, just bolted together in slightly different ways. Commands versus messages, and I talked about this a little bit. So the notion of update that we've seen so far is that update takes in a message and a model and spits out, well, this is a very misleading slide until I put this on. Update's going to return a model, and I think this may be a bug, and I apologize about that. But one of the things update can produce is a command, and a command, again, is this box for messages, and these messages come out the other side. So this is the Elm runtime's biggest job, is to take commands, which are requests for things to be done, do them, and then return a message telling you the outcome of that, or some result of that. And so you ask the runtime to do stuff, so it's a command, and that's why it's called command, do this. And then we get a notification from the runtime that's piped into our update, where we then munge our model. And the quote that kind of works for me is this: we create data that describes what we want to do, these commands. We tell the runtime, I would like this to happen. I would like an HTTP request to be made to some remote source or something along those lines, or to render some ASCII doc. And then the Elm runtime does the dirty work. It knows then how to talk to JavaScript stuff. It knows how to do real work, and ultimately return some result to you on the other side. So this is a key cycle to keep in your mind as you were working with Elm. One of the other bits of magic that makes Elm actually function in a practical sense is the use of virtual DOM. Is everybody familiar with the basic idea of virtual DOM? Yeah, it's taken naively, the Elm architecture is abysmally slow, right? You take in a message and a model, create a brand new model, re-render that, and that you can imagine would just be horribly, horribly slow, but that's not actually what happens. What we do is we re-render a virtual DOM every time. So we start off by building a virtual DOM. That's what these HTML things that we've been seeing are doing in our views. So it's got a div and an H1 and whatnot. And that does, the very first time, oh, I'm sorry, I thought I heard somebody say something. That gets rendered to an actual DOM, so that the structure that your browser is using as the backing for all the stuff it's showing. That's the document object model, I think it stands for. I then go through my Elm architecture loop, where I copy the old virtual DOM, very fast operation, probably using all sorts of caching and tricks like that, because we have a bunch of immutable data structures, so we can do that. We can pull these tricks off in Elm. I add some new element to my virtual DOM, and then just the diff gets rendered in the actual DOM. So the speed comes from the fact that I'm only ever re-rendering the diffs. And this is, virtual DOM is a technology that's it's not unique to Elm. It's used in many other places, but this is the fundamental idea. You do the big work in these really fast data structures that can share and all that kind of stuff, and then only when you know the small deltas that you then inform the browser what to do. And so that's how Elm is able to be competitively fast, and not just competitively fast, but faster than almost everything else out there. So I know this is really hard to read, and I didn't come up with these numbers. I'm quoting them from Elm papers and things like that. But these are average time in milliseconds to render some page, or this to-do MVC, which is kind of a benchmark for single-page apps. You see, Ember and Angular take that long and that long, but Elm takes that long. The only one faster than it is Mercury. I've never even heard of Mercury, so it can't be that relevant, right? Has anybody heard of Mercury? I don't know what it is. But Elm is super, super fast because it's leveraging so well immutable data structures, virtual DOMs, and it just has nice hand-optimized JavaScript code in the base of it. It's super, super fast. Angular is wonderful in many ways, but it suffers from the fact that it has to deal with all the dynamism of JavaScript all the time. It can't take the shortcuts that Elm can take. So this is one of the huge benefits of applying proper computer science to the problems we need to solve. They're solved here, and this starts to seem like a real mess after a while when you compare it to what could actually be done in the real world. And this is one of the things, not the performance per se, but the fact that the performance is coming from the application of a broad pool of knowledge that doesn't seem to be applied that well to these other things. people who know JavaScript, I don't want to denigrate them, but they very often have approached programming from a non-CS background. They don't know what's possible. It's only when you get people who go to Harvard and study CS and know about the web that you end up with things like Elm. It's probably unfair on many levels, but it feels that way. There's just another benchmark here showing that Elm is, again, very competitive, even against optimized versions of these other technologies. Apparently, optimizing Elm code is very straightforward. From the implementer's point of view, making the compiler produce optimized code is straightforward, again, because all the assumptions they can make about immutable data structures and things like that under the hood. So these are interesting articles worth reading, and they go into more detail. Maybe it'll be more convincing than me just talking about it. So I've shown you the Elm architecture. Let's take a look at that in miniature. I have a bunch of code. Oh yeah, and we're going to look at yet another piece of technology. Who here has used IPython notebooks in the past? Okay, it's originally a Python technology that lets you kind of intersperse markdown and then code that can be executed on the web page, and it's very nice for sciencey stuff, and it's great for some kinds of demonstrations. I've written a kernel, which is a language-specific back-end for, well, I should call it Jupyter now, because Jupyter's the front end, and there's all these kernels in the back. So we have IPython for Elm now, and that's what I'm going to show you here. Right, so this is what a Jupyter notebook looks like. So the complete Elm architecture example, let me make sure that all the outputs are cleared. Right, so at the very top of your Elm program, you'll generally have all your imports. And so here we're pulling in a bunch of HTML stuff, events, some platform stuff, and string. Okay, so we have to reverse strings, yeah. So nothing terribly exciting there. Dump that into the kernel. Next, we define a very, very simple model. Let me bring that to the top. So our model in this case is not a record, it's just a string. And the program, I guess I could tell you, is a program that lets you enter a string into a text box and then shows you the reverse of that string beneath it. So it's another mind-blowing example of code. But our model is super simple on purpose. It's just a string. Execute that. And these messages then, these are the messages that get pumped into our update function, are all the ways that our model can change, all the ways we've decided to define change on our model. One is we can set it to some new string, or we can clear it, right? So the set message actually comes with a new string that becomes our model, and clear is just a command to the update function to set it to null. I guess we could, in some sense, have just reused set message, but I think this is a better teachable moment to have two messages. So pump that into the kernel. Our update function, okay, things are getting more interesting now. Update takes a message and a model, and what it returns is a model and then some command, and we've kind of seen that rendered pictorially. So remember, our model is just a string. So message comes in, and it can be one of two things, set message or clear message. If it's set message, it comes with a new message that becomes our model. So we just spit back that M. I'm not sure how readable that is, but we just return that new M as our model. That has become the model for the system now. And we don't have any messages or commands we want to send out. Clear message is just as simple. We just set the model to empty string. It's very, very simple. And you can reason about this in its entirety without worrying about the view at all. The view handles what it does, update handles what it does, and if everything compiles, then it's very often going to work correctly. The view function is just a bunch of HTML. I don't really need to go into the details, but if you know HTML, again, this should be quite readable even if you don't have any real Elm knowledge. You have a div. It has two inputs. The first input has a placeholder that says text to reverse, so it'll tell you to please enter some text. The value of that input is the model. It's just a string. On input, so if anybody pushes a key, it's going to fire off set message with whatever the value of the input happens to be at the time, and we style it a bit with some CSS, which we don't need to look at. And then we have another input, which is the reversed version of the model, right? So the value of that is string.reverse on the model. This is great. I'm here using like a proper programming language to set up my display. I'm not having to jump through directives and scopes and stuff like that to kind of reach under the hood to find JavaScript. I can just say, I'm just using Elm code, which then produces HTML. This feels like the right direction. Rather than starting at HTML and reaching in and doing code, I start with proper code, the stuff where we can do real programming, and then turn that into HTML. input style, and it's disabled, so they can't enter text in there. And if you want to see this is the styling here. There's a lot of effort in certain parts of the Elm community to come up with a good type-safe CSS system. So I don't know how good any of those are right now, or if they'll ever be any good. So very often you end up with just strings for your CSS, which is reasonable. Or you can just have it refer to a CSS file, which is actually more common in large projects, of course. Finally, we may wire everything together in main. So we've told it, initialize yourself with an empty string. That's our initial model. No messages need to go out. View, update, no subscriptions. We don't care about anything like that. And a little note, okay, this is what a comment looks like in Elm --. The way the kernel works right now is a bit hacky. When it sees a cell that ends in that string, then it knows to take all the stuff we've seen so far and compile it into a program. So when I push the button on this guy, the star means it's thinking, means it's compiling. The kernel's in the background downloading some stuff. So actually, there we go. Okay, it worked. Wonderful. It could have failed because if the network was bad, I couldn't download the packages I need. So, okay, here is the moment you've all been waiting for. You know, a man, a plan, a canal, Panama. Right, that's reads the same forwards and backwards. It's a palindrome for those who aren't up on their palindrome lore. But that's a little bit hard to read, so, you know, llama, right? That's it. So every time I push a key in this text to reverse field, a message is being sent through that loop with the new value, which is getting set to my model and then rendered to the screen. And if I push clear, it sends the clear message, which then updates the model. It's all, okay, this is a toy example, but it's super fast and really easy to understand. So you can get this. I'll have links to all this stuff at the end of the presentation, but you can get this, the code for this notebook and run it yourself if you want at home. So that is the Elm architecture, which really is that's the kind of the box that all Elm programs kind of sit inside in the real world. Sorry. I was talking very loud last night at a bar, so my voice is starting to give out a little bit. Right, so I told you we would look at some specific techniques that you almost always need to use in real Elm programs. One is talking to the web. I can use this, can't I? So in the real world, things break, right? The web server might be down. You may have sent a badly formatted message. Who knows what? So to capture that notion, there's a type called result, which is in the standard library of Elm. It's a union type, you can see here, and it's parameterized on two other types, an error type and a value type that you provide. And its constructors are OK and error, which you probably imagine this means that everything worked OK, and they give you the value that the computation produced. Otherwise, if there is an error, you get this coming out. This constructor is used, and they tag on whatever the error is. Typically, error is a string, just to give you some string indication of what failed, right? So, of course, we need this if we want to send an HTTP request, because this is what the HTTP library uses to tell you when things work or don't work, right? So everything worked, something went wrong. So this is a typical use of the result type. So send is part of the HTTP library. So I've used it as is request. So you construct a request by saying, I want to do a get. And so you call the get function, and it gives you a request back. You pass that in to the send function. And this, if you know how to read these kinds of languages, this is a function fundamentally. This is saying, you also need to give me a function how to take a result and turn it into a message. And remember, message is the type that you've defined. That's the type that's flowing through the system into your update functions. So you've told it now, no matter what happens with this get when you execute it, error or good, I know how to turn that into a message. And you pass it into send, it tries to do the HTTP request, and that results in either an OK or an error, which you know how to translate to a message, and you end up with a message flowing into your system. And so typically, well, we'll see a full example here. Yeah, this is the translator function fundamentally. The parentheses are not required, but they're almost always used as an aid to humans so that we can see this is intended to be thought of as a function. But because of currying and partial application and all that kind of stuff, it doesn't necessarily have to be that way. You can be very fancy and confusing if you choose to. We'll see this all used in a bit. Sorry about this. The other part, because almost all web interaction in Elm touches JSON in some way, shape, or form. You're getting JSON back from a server to then render to the screen. People get tripped up on JSON decoding because it feels a bit backwards maybe compared to how they've done it in other languages. The core idea is you have some notion of a decoder that can decode JSON into a type A.
integer, list, your record type, whatever. So you very often start with primitive decoders, so they provide an int decoder that knows how to decode ints. You often combine those into more complex types, so you can create a type called, this is illegal, actually, this syntax, but it gets the point across that list int would be of type decoder of list of integers, right? So it would know how to take JSON representing a list of integers and produce an actual Elm list of integers. They have helper functions that know how to extract elements from an object in JavaScript. So you might get an object in JavaScript that has a prices field, which you say has a type of list integers. The mapped to value is a type of list integers. And so you can use field with prices in this to create a decoder for a list of integers that actually pulls the value from the prices field. Okay? So we're getting more and more complicated. And then finally, if you have a type called, say, stock, for example, and this is the prices of the stock here, you can map your stock constructor, your record type, over this decoder, which remember pulls prices out and turns them into a list of ints, and now you have a decoder for your stock type. So this is the common pattern you follow. You start by saying, okay, these are the primitive types in my record, and ultimately end up constructing a decoder that knows how to make your specific type for you, and then your type flows through the system. So it's, okay, this is great. We have decoders now, but how do we actually use the decoders? The trick to that, oh, I should actually point this out. JSON decode is in the standard library. And it's a bit clunky, and there's another library called JSON decode.pipeline, which makes it visually and I think mentally easier to bolt all this stuff together. So if you start doing a lot of JSON work, look into decode.pipeline, and I think you'll thank me in the long run. It's not part of the standard library, though. But the magic sauce that brings it all together is a function called decode string, which takes a decoder of a, so stock or listed int, whatever, and a string, this is your JSON, and gives you back a result. We saw earlier, right, that maybe has an A, maybe has a stock, or maybe has an error because what you've given it is not actually legitimate JSON, or is not legitimate JSON for one of your stocks. So this is where results start to show up. So this decode string could succeed or fail, and it's going to report to you success or failure via this result object. So results are used very, very widely in the library for places where things can go wrong. The flip side of this is encoding JSON. Fortunately, this is much, much simpler. The goal is you want to convert your primitive objects, well, your objects into things called values. This is this type in the encoding library. So there's an int encoder. You give it an integer and it gives you back one of these values. You can compose that with, you have lists of values, and so this knows how to take, a list of things and give you back, a list of any values that you probably got using one of the primitive encoders, and it gives you back yet another value representing the full list. And you can encode those into strings using the function called encode. So there's less mental arithmetic needed to get this all done, and people don't generally trip up on the encoding part. But the decoding part, it's a very common theme on the discussion lists, so I thought I should cover that. And so if I wanted to encode ints, for example, it would look like this. Takes in a list of integers, first maps JSON encode int over each of the elements, and then I compose that with two other things, encode that to a list, and then encode 2 is just the indentation, right? So it's producing some nice looking JSON. Don't worry if that doesn't all make sense. It didn't land very well, I think, the way I said it, but you can look at the slides later. Encoding is very, very simple. So how do we combine that then with HTTP? Because very often you want to make some request to some web server. It's going to spit back some JSON, and you're going to decode that and turn that into something you use inside your program. Right, so this is inside my update function. Very often somebody has pushed a button on my UI, and that's sent a message to me saying, oh, you need to go fetch some data. So in my update function, I say, well, okay, that's going to result in an HTTP GET. So I tell it the URL and the decoder that I want to use. Whatever data comes back from there, I want it to be decoded using this decoder. That's going to return a request object. And the request object is the thing that I then pass into send along with a message type. So HTTP send is given a request, which is part of the HTTP library, and data fetched I've defined up here as a message. So data fetched it carries with it a result on failure has an HTTP error, and on success has a data, which is whatever I've defined here, okay? The end result being that this is sent, the command goes out to the runtime, it makes the request. On success, I get a data fetched coming back into update with OK data. So saying everything succeeded, you can pattern match on OK and then extract your data from that and pass it, pass it around your program. Or the other option is that I get an error message coming in saying, oh, things didn't work, and here's the HTTP error that you got. Show it to your user or do whatever you want with it. But because of the way the language is built, again, you're forced to handle every single case because you have to be able to deal with the result that comes from HTTP send. Your message has to know what to do with that type, and every bit of your code is forced to deal with every permutation of that type. You can't leave holes unfilled in Elm, and that's part of what makes it so robust. So did that work at all, that explanation? I feel it was a bit stilted, but it's, yeah. This picture, when I was finally able to draw it, I felt like I had kind of leveled up a little bit. It kind of puts all the pieces together. Another important thing is JavaScript interop. There are a number of different times and places where you want to interact with JavaScript. One is this notion of flags, which I didn't have to pay attention to for a long time, but it's actually quite useful and important. Flags are fundamentally how to get JavaScript code, some JavaScript data structure, into your program at startup time. So typically your Elm code is embedded in some little bit of JavaScript, and you can create a little structure there that maybe reads from a file or talks to a database and builds up some initialization data and then passes that into the program, to the main function. So here in JavaScript land, we've created some object called flags, which we're going to be in debug mode, and here's a connection string to a database. We create our Elm object, we find the place in the DOM that we want to mount our Elm program, and then we embed it. So we say my app, embed at mount node, and pass in the flags. Okay, very straightforward. In Elm, it looks, well, it's the receiver of this data. We've got a type, a record called flags, which, if you compare these two, are very, very similar, right? This is a Boolean and a string. We said we're an HTML program. We want to receive some startup data from JavaScript of type flags, which is what's passed in here, and then we're going to pass that, into our initialization routines. So that type maps to that, and these flags ultimately end up in your initialization routines, and you can use them to do whatever you want. An example in the ACCU app is which endpoint do we go to receive the schedule information for the conference, right? I can configure that to look at a number of different places. And I have some JavaScript that just reads that at the .env file, pulls that information out, and then passes it in through these flags. So this is very widely used in most real-world programs, so it's good to know about. The other very common way of interacting with JavaScript is through what's called subscriptions. And subscriptions can be thought of as publishers of messages from JavaScript land that you want to deal with in your program. So the canonical example is a WebSocket. You may down in your JavaScript have a WebSocket that's listening, getting data from some web server, and you want, as messages arrive on that WebSocket, to pump them up into your Elm application. So I have this subscription here that, well, let's approach it the other direction. When I build my program, I tell it my subscriptions are this function up here, and that function has to take a model and then return, well, a subscription, this subtype here. And all it means is that when this WebSocket spits something out and something's available, I'm told the runtime, please construct this message type, which I've defined up here, to carry that string and pump it into my update function. So now my update function is handling not just button clicks and stuff, but also stuff that's happening sort of asynchronously in the outside world. And so subscriptions can cover all sorts of, well, any source of data that might come from the outside world. That's what subscriptions are all about. And you have to set them up at startup time. They don't come and go as your program lives. You establish that all at the very beginning. Yeah, so we tell it what type we want. We give it a specific constructor to handle specific kinds of subscriptions, and then we make sure everything is wired together. I guess I should point out, this makes it look like you can only have one subscription, and that's kind of true, but you can also have what are called batch subscriptions. So if I have several things I want to listen to, I can kind of glom them all together and say, treat these as a single subscription, and that goes in here. The final way of doing JavaScript interop is what's called ports. And I screwed up the animation on this slide, but ports are defined in Elm. So I have a module that I have to tell it is a port module, because this means that it's going to have to generate some special JavaScript code for me. Ports can be one direction or two directions. Well, all ports are one direction or the other, but you can have both kinds. So in this case, we've got a port called check. And check Imagine this is a spell checker, which is why it's called spelling. I'm going to ask JavaScript to use some fancy JavaScript spell checker to do my spell checking for me. So I've told it, you're going to take a string, and that's going to result in a command being sent down to JavaScript that's going to then result in a message coming back with some information that I can use. So this is an outgoing port, and the code for an outgoing port looks something like this. So I import my spelling application. It has an attribute called ports that's going to have something called check because I've defined that there. And in JavaScript, I subscribe to that port by just giving it a function that's going to then be passed the string that comes into the port. And then I do whatever I need to do. And here I do the spell checking. This other port is an incoming port. And you can see it's incoming because it ends in a subscription. So I've defined a new subscription, a new way of getting data out of the runtime. And it's called suggestions. And this is the result of the spell checker saying, well, this could be this word, this word, this word, or this word. And it's going to give me back a list of strings. I provided a function that takes a list of strings and results in a message. And the whole idea is that down in JavaScript land, when it's calculated the suggestions, it goes to the ports again, finds the suggestions port, and says, oh, please send this list of strings back into JavaScript. Back into Elm. And this function I provided to the subscription constructor knows how to take a list of strings, construct a message, and then pipe that into my update function. So again, it's like all roads lead to Rome, all routes lead to the update function in JavaScript, and it's an inviolable kind of rule. You don't often need to use JavaScript interop at that level. Very often, if you have to interact with some JavaScript library, somebody has written a wrapper for you, or written a library that handles it for you. But sometimes you have to. We had to do some native interop for the ACCU app, which we can perhaps see here. So before I dive into the ACCU app, are there any sort of outstanding questions, any blank spaces in the map? I know it's a lot of information, and partly that's just the nature of the talk, and partly I talk a bit fast sometimes, so it's maybe overwhelming. I apologize for that. So we'll take a quick tour of the ACCU app. You may not have noticed this or known this, but the ACCU app actually looks exactly like downtown Austin, Texas. And there are all these highlights on the map. Yeah, so the university's here, and I went to grad school in here somewhere, and this is the Capitol, if you want to yell at Texas lawmakers, which you should. They all work there. Some good restaurants down in here. Okay, so the first thing we want to look at is index.js. So all Elm applications, as lovely as Elm is, are embedded in some at least thin wrapper of JavaScript. And that's the place where you set up your flag, that's the place where you find the mount node in the DOM and all that kind of stuff. So index.js is where we want to start. Let's go to Emacs, of course. And this is in the ACCU 2017 Elm. Is that it? Yeah. Right. So this is the entirety of our index.js, which is essentially the root of the entire application. Now, those of you who are eagle-eyed will recognize this is not actually really JavaScript. This is Webpack, but basically JavaScript. So we require a few things. Actually, ignore these requires. That's the Webpack stuff. This is where it gets interesting. Oops. So that's just a touch hard to read there. So we require main.elm. This is also a Webpackism. It's saying go find the file main.elm, compile it, and give me the JavaScript back and bind it to this thing called Elm. So Webpack is actually a very convenient technology to use with Elm because it knows how to do this kind of stuff. We then look up the mount node. So it's just some div called main somewhere in the HTML. We could look at that, but it's not very exciting. Here we do some local storage interaction. We look up any bookmarks that we might have made in local storage. So we have a string that's if you know how local storage works, it's a dictionary, basically mapping strings to stuff. We pull that stuff out if it exists, otherwise we default it to an empty list. We construct our flags here. The two things that we want to pass into our program are any bookmarks the user's made. So if you click the little flag on the app, I'm creating bookmarks there. And then this API-based URL, we pull that out of a file, and it tells us where to drag schedule information from, right? And then this isn't strictly necessary using a timeout, but it tends to make things work a bit more robustly. I construct my app object by calling embed on the mount node with the flags. And this is calling into our main function at this point. And then I look up on that app a port called store. And the store app is, when you click that little flag on the proposal cards on the UI, we send information back down to JavaScript to this port saying, please save this, so that when the user comes back later on, they can find it. So that's what's going on here. We subscribe to it, and we're just going to store stuff in local storage. So that's the index.js. It's pretty small, but this, I think, this is useful to know if you start setting out to write your own programs. How to bolt these things together is not entirely clear or obvious from the documentation I found, but having an example that does it all really pulls things together. So don't memorize it right now, just know that it exists, and you can find it when you need to. So this is a bit clunkier. Okay, fine, that brings us then to main.elm. Right. So here we have a bunch of imports that aren't terribly exciting. We have the flags object. That is the analog to what we just saw in index.js. Here, because we have internal navigation inside the application, we use a navigation program with flags. Right? This is just saying that our init is going to take in some flags, and it's going to take in a location, which is, won't go into details, but essentially where do we start the app at? What's the starting URL inside the app? We do a bunch of things like initializing the model, but using things that we drag out of the flags. And then we pass back our model. Remember, the init function is supposed to provide you your initial model, plus any commands you want to run at the start. And here we're going to do three things. First, we have to initialize MDL, the Material Design Light library, which is doing most of the UI. And we want to make two requests to fetch proposals and fetch presenters. So at the very beginning of our program, we create a model, and we spit out two commands to HTTP to fetch some data. And the rest of this is pretty unexciting. We subscribe to Material MDL stuff because it's producing a bunch of messages down in JavaScript land that we just kind of pipe through to MDL. And our view and update are very unexciting. So the next thing that's worth looking at is the model. And this is, like I said, when I start writing an Elm program, I typically start with the model because that's kind of what I know the most about to start with. So a lot of bouncing back and forth here. Right. So I've kind of broken the model into two sort of pieces. One is can you guys read that? Not really. Right. So the view model, all the view model's really keeping track of is whether or not, as I mouse over cards, I want them to kind of pop up a little bit. So I have to keep track of which of them are supposed to be popped up at any given time. So is there any proposal that's supposed to be raised? Well, maybe there is, maybe there's not. Is there a presenter that's supposed to be raised? Again, maybe, maybe not. I then have a view model embedded in my overall model. So this is the main model for the program itself. You can see you've got a list of proposals, and we'll look at the type of proposals in a second, but it's terribly unexciting. List of presenters, again, not terribly exciting. The API base URL, the bookmarks that we've dragged out of local storage, a material model, which we won't talk about, and then the route path, where we are inside the application, is modeled as a union type, and then the view model itself. And some utility functions, but the rest of this is not terribly exciting. What's important is the model we just looked at and the function we have that provides an initial model. So this is going to take in some values that we dragged out of the flags, construct some initial model, and that's where our program kicks off at. So the flow is almost mind-numbingly stupid, right? You start off with some empty model, and we've sent two messages off into the ether, hoping you get data out of the web server. Eventually, those are going to come back, and as they arrive, we just start replacing our model with data that we've drawn out of these web servers, or not. Maybe we got errors back. So we know we start off in a nice, stable state, because we provided that here, and as data arrives, we just dump it in there. And there's no having to think about how these things interact. You just know that it's going to happen magically for you. I think maybe we'll look at one more thing, because we're kind of running out of time. That's my fault. Message is not very exciting. Update's not very exciting. Comms is reasonably exciting. This is where we do our HTTP stuff. So you can see I import here this, it's a bit hard to see. I import the HTTP library. And this is the only module where we refer to HTTP throughout the entire program. So I've wrapped up all that communication stuff inside inside comms. So at the beginning of our program, or if you push the refresh button, we end up calling the fetch proposals and the fetch presenters functions. Those take the API base URL, which is provided to us via flags, knows how to construct the URL, makes a URL request, and then sends it. So send is exactly what we were looking at before, the thing that knows how to do the work and provide you then with the result of either OK or error. And then you see that these are returning types of command, right? And command, the only thing command does is get routed down to the runtime to result in a message. So we've basically wrapped up all of our communication, all of our HTTP stuff, or maybe not HTTP, I mean, the user doesn't know at this point, wrapped it up in this nice little API where they give us a model and things happen. And then they can react to those things in one way, and that's inside their update function. So I keep repeating this over and over again because it's really the only way things happen in Elm, and that's the lesson that I'm trying to drive home. So there's not a lot of communication in this program, just these two. And I think, we'll look at one more. JSON is boring. Routing is pretty dull. Search is dull. Well, the one I want to show you is ASCII-Doc because I'm a little bit proud of it. So, yeah, let's find it first. OK, ASCII-Doc.elm, very small. So when you submit a proposal to ACCU, you're allowed to use ASCII-Doc, which is a text format that can be rendered in very fancy ways. And it's very similar to Markdown. So when I originally wrote the ACCU app, I thought it was Markdown, and so I was using a Markdown renderer, which was easily available in the Elm world. When I found out later on that actually it's ASCII-Doc instead of Markdown, we had to do some work to find ASCII-Doc.js and write the bindings in Elm to talk to that. And so that's what we're doing here. So we've got a module called ASCII-Doc, or ACCU-schedule.ASCII-Doc. It imports something called native.ASCII-Doc, which we'll look at in a second. But fundamentally, it's just a JavaScript file that embeds the ASCII-Doc.js stuff. So the parser that knows how to take ASCII-Doc and generate HTML. And we expose a function called toHTML that takes a list of attributes. You can think of those as HTML attributes. And then a string, which is your ASCII-Doc string, and generates, through a native call down here, a bunch of HTML, which then comes out the other end. I basically looked at how the Markdown parser worked and cloned it for ASCII-Doc. So this is then an Elm face onto some native code. So what does that native code look like? It has to exist in something called native. So we've got ASCII-Doc.js here. We won't go through all of this, obviously, but the point is that this is all JavaScript now. And you end up writing, this is sort of compiled Elm speak, so to speak, these dollar signs and stuff. If you look at the code that comes out of the Elm compiler, it all looks like this. This is how it represents namespaces and module names and all that kind of stuff. And so we have this function called toHTML, which is what we're actually calling from our Elm code. And then we know how to plug it all into Elm by, I think it's this, here we go, return this thing back to the Elm runtime saying, toHTML, hard to see from the back, I guess, is a function of 2 arguments. This F2 is provided by the Elm runtime. And when somebody wants to access it, Elm is going to expose, the Elm runtime is going to expose this back up to Elm. So we've made an Elm function here, in a sense. We've informed Elm that there's a function called toHTML in this JavaScript file that you can then call from Elm itself, and it just routes it to this toHTML function, which does the hard work of finding ASCII-Doc.js, doing the parsing, doing the generation, and so forth, and then it spits some HTML back to us in Elm, which we then blow up on the screen. So I think that's the last thing I want to talk about. There's, you'll have access to the slides and all of the source code. You can view it at your leisure. The view code, I haven't measured it, but the view code is probably by far the biggest single element in terms of source code lines in the program, but it's the most unexciting one too. All it does is just make it just takes a model and spits out a bunch of HTML. So it's worth browsing through to familiarize yourself with it, but there's really no point in us looking at it. Austin's a wonderful city. There's a restaurant right here. They make this tobacco-infused tequila, which sounds really disgusting, but if you get a chance, go to La Condesa in Austin and have that stuff, and you will thank me. And eat the fried crickets as well. It's a heck of a meal. Really, really good stuff. Oh, and the best barbecue, possibly in the entire country, is right there, Franklin's. You have to wait in line for 4 or 5 hours to get it, but my God, is it good. Okay. Anyhow, caveat emptor, well, caveat Elmtor, spending too much time with Chris Oldwood. Elm has a lot of potential. I hope that I've kind of sold it, but I don't want to have you leave the room thinking that it's all roses and wine, because it's a young, small language with a relatively small number of users, and so it has some rough edges and rough edge use cases and so forth. The language and the core are evolving. When I started using Elm, it was at 0.16, it's now at 0.18, and that transition was brutal, because like all sorts of stuff broke. They've claimed that they're going to stop doing that, and things seem to have settled down quite a bit. I think that if they try to do it again, maybe they'll get one more out, and then they're just going to lose all their users. So I don't want to scare you off. I don't think it's going to change that much in the upcoming changes to the language. The language is going to continue to evolve, but it's not going to evolve in breaking ways, or horrible breaking ways. Best practices are very far from being settled, and a lot of the discussion on the discussion groups is about how to do componentization. Should we do componentization? Is that just philosophically opposed to how Elm is supposed to be written? How do we do all sorts of stuff? And so it's interesting and fascinating. If you want to see how languages are built, it's really worth getting involved, but there's other places you can do that as well. So don't use Elm just for that reason. And be aware that you may be just doing things wrong, and you'll only find out in a year when the luminaries wave their wand. There's the risk of bust factor. If Evan gets tired of doing Elm, I don't know who would write the compiler. There are other people certainly who could do it, but I don't know if him being the hub of the wheel would just cause the whole thing to fly apart. Who knows? But he's currently being paid, as I understand it, to write the Elm compiler, so it's well supported in that sense. The tooling certainly has room for improvement. In fact, that's the kind of thing you could get involved with. I mean, things like the Jupyter kernel, we had to write because I wanted one and one didn't exist. Autocomplete and stuff like that is pretty sketchy for the most part. But I guess that also means that it works as well in Emacs as it does in everything else. So I can continue using Emacs for it, and I don't have to feel like I'm losing. Yeah. I will never stop using Emacs. It really doesn't matter how fancy the other IDEs are. And there's the fact that it's just different, right? If you're working on a team and they all know JavaScript and they all know, Backbone or something, coming into a meeting one day and saying, "Hey guys, we should use Haskell. We should use a functional language with data structures you can't change." They might just rebel. So I guess the approach to that, if you have that problem, is to just do it anyway. Take a small part of your website and just do it anyway, right? And you can get a long way. What's easier to ask forgiveness than permission, right? It's true. So you can approach it that way. But you're going to have to deal with the fact that it's just an alien thing to a lot of people, a lot of programmers. Here are a few links. Take a picture if you want, but I think the PDF for this will be available later on. So you can find all the code examples there. I misspelled Jupyter. I properly spelled Jupyter there, but it should be with a Y. There's the kernel there for Elm, which is an ongoing project. If you want to get involved in that, I would love some help. And there is the repository for the Elm app that we're using here, and I could definitely use some help on that, because get it to the point where it can be used year after year and present and show more things. Right now, it's pretty bare bones. We don't show keynotes, we don't show plenary sessions, we don't show quickie slots, anything like that. We could really improve it. So if you want to dip your toes in Elm, this may be a good way to get started. It's all there. You just need to show up and make some pull requests, and I'd be happy to process those. I was told to remind you, don't forget to put a green card, and there's 2 boxes, one at each door, so yeah. The red cards and the yellow cards are just for decoration. You're not supposed to use those. Finally, thank you very much for your time, and I'm happy to take questions.